This is the second of 4 videos for this course. Now we have enough information that we want to get to understand the Schrödinger equation and how the things that we have covered for particle in the box are solutions of the Schrödinger equation. So we're going to start with the classical wave equation. For classical vibration and waves, we have some measurable quantity, let's call it u, representing the amplitude of the wave. The height of the wave, the pressure of air, the electric field, etc. And we have a wave equation relating some time derivative of u to some spatial derivative of u. For a traveling wave propagating in one direction only, the classical wave equation is the second derivative of u with respect to time equals the velocity squared times the second derivative of u with respect to position squared, where v is the positive phase velocity of the wave. This classical wave equation is a second-order partial differential equation. If you don't know calculus and differential equations, you don't really need that knowledge if you trust the solutions that I will give you. But it will be helpful to understand in words what the derivatives mean. So it will be helpful to at least know that the first partial derivative of u with respect to x, it's the rate of change of function or quantity u with respect to position variable x, ignoring any explicit time dependence. It's that value, that rate of change, at some position x in time t. The second partial derivative with respect to x is the rate of change of the rate of change, which is a measure of how much u is curving in space toward or away from the x-axis. There is a general traveling wave solution to the classical wave equation. U of x and t is some constant a, arbitrary real constant, times some function f, an arbitrary function of x minus vt, plus constant b times arbitrary function g of x plus vt. F of x minus vt is some wave traveling in the plus x direction at constant speed v. G of x plus vt is some wave traveling in the minus x direction at constant speed v. When the wave is a pure sinusoid with a single wavelength and frequency, we usually express the traveling waves in terms of sine of 2 pi x minus vt over lambda, traveling in the right direction, and sine of 2 pi x plus vt over lambda, traveling in the left direction. For light, in the black body cavity, the velocity was c, the speed of light, and we can use some math to express the standing waves that we used earlier in the lecture in terms of two traveling waves traveling in opposite directions. The quantum mechanical wave equation for matter waves. It turns out that the classical wave equation is not correct for quantum mechanical matter waves. We will examine the Schrödinger equation for matter-particle waves. We will see that the Schrödinger equation includes the imaginary number I, square root of minus 1, and that quantum mechanics uses complex numbers and complex exponentials. It turns out, we won't prove this, that the wave function for a free particle of non-zero mass m, free to travel forever in one dimension, the plus x direction, for all time at constant non-relativistic speed v, so constant non-relativistic momentum p equals mv, with no barriers, no disturbance, zero net force, zero acceleration, constant potential energy, which we can take to be zero. It cannot be expressed as a simple real sine wave. for a matter wave, a free particle matter wave, and it must be expressed as the complex exponential capital psi of x and t equals e to the I quantity px minus et over h bar, where I is square root of minus 1, the imaginary unit, e is base of natural logarithms, p equals mv is the momentum, constant non-relativistic momentum, kinetic energy E is p squared over 2m, constant non-relativistic, h bar is the reduced Planck's constant, h over 2 pi, where h is Planck's constant, with dimensions of energy times time, or equivalently, distance times momentum, or angular momentum. For this free particle matter wave, we have the following constants. Wavelength lambda is Planck's constant h over momentum p. This is called the de Broglie wavelength, or the de Broglie wavelength. And this relation is called the de Broglie relation, proposed by physicist Louis de Broglie for matter waves in 1924, the year before Schrödinger developed the Schrödinger wave equation. Wave number k is 2 pi over lambda, which is momentum p over h bar. Angular frequency omega is e over h bar, which we can do the math and we get velocity over 2 times the wave number. Phase velocity is energy over momentum, and it's velocity v over 2. But group velocity is the derivative of energy with respect to momentum, and that is velocity v. Let's replace energy E with p squared over 2m. We get capital psi of x and t is e to the I quantity px minus p squared t over 2m, quantity divided by h bar, for a free particle wave function. X and t are independent variables, and momentum p is constant for this problem. Let's take some partial derivatives of the wave function with respect to x and t. If you don't know calculus, just accept the results that I'm going to give you. If we take the derivative of psi with respect to t, we bring down a factor of I times quantity minus p squared over 2m divided by h bar. So the time derivative of psi is minus I p squared over 2m h bar times psi. If we take the derivative with respect to x, it brings down a factor of I p over h bar. So we get I p over h bar psi of x and t. This gives us a way to define a momentum operator, p sub x, and we'll denote this as an operator by having this caret or hat above p to tell us, remind us, this is an operator. It's not a numerical value. Operator p sub x, we're going to define it as h bar over I times the partial derivative with respect to x. If we use that operator and operate on the wave function, we get h bar over I, partial derivative with respect to x of the wave function. That brings down, we saw here, it brings a factor of ip over h bar times the wave function. The i's cancel, the h bars cancel, and we're left with p times wave function psi. Now this p is the constant value of momentum for that free particle. This p sub x hat is an operator. This value of p is the constant momentum for this special free particle wave function. The momentum operator extracts the momentum value from the free particle wave function. We say that momentum value P is the eigenvalue of the momentum operator P sub x hat for the free particle momentum eigenfunction e to the I quantity px minus et over h bar. Now we could take a second derivative with respect to x. The first derivative gives us a factor of ip over h bar, and the second derivative gives us another factor. I times I is minus 1, p times p is p squared, h bar squared. So this is the second derivative of psi with respect to x, and t is minus p squared over h bar squared psi of x and t. Now we can do the following math steps to end up with a wave equation for free particle matter waves. We can rearrange it so we get minus p squared psi is h bar squared times the second derivative of psi. We can use the time derivative and move some of its factors to the right side so that we get the time derivative of psi is I h bar squared over 2m h bar times the second derivative of psi. And if we pull the I and this h bar over to the left hand side, we get I h bar first time derivative of psi equals minus h bar squared over 2m times the second derivative with respect to x of psi. This is the correct one-dimensional wave equation for a non-relativistic free particle. To check, we plug the free particle wave function into both sides of this matter wave equation. If you plug it into the left and do the math, you will get E times psi. If you plug it in, if you do the operation on the right, you will get p squared over 2m times psi. And the energy is p squared over 2m for this free particle wave function. Like the classical wave equation, this matter wave equation has a second order spatial derivative. Here's the second order spatial derivative. However, unlike the classical wave equation, this matter wave equation has a first order time derivative, not a second order time derivative. Also, it has this imaginary number I associated with the time derivative. This undoes the effect of a minus I that comes from doing the time derivative operation. It has a minus sign associated with the second order spatial derivative. This undoes the effect of a minus sign that comes from doing the spatial derivatives. The complex exponential is the eigenfunction, not the real sine and real cosine functions. And it has h bar in the matter wave equation. Every energy solution and wave function will have h bar in it, the reduced Planck's constant. This is what sets quantum mechanics as the physics of small systems, such as atoms. H bar sets the energies and sizes of small systems. This matter wave equation differs from the classical wave equation, has a first order time derivative instead of a second order. It uses and requires complex numbers and complex exponentials because the particle has mass and we're only seeking a non-relativistic wave equation, and we're ignoring the particle's rest mass energy, mc squared. There is a relativistic wave equation, but it has other complexities, and it is only used when non-relativistic quantum mechanics is insufficient. So we won't cover it. Now, there are issues with using the free particle solution, which would be explained by courses and books, but our interest in the free particle was only to help get us to this matter wave equation, to get us to this point, the Schrödinger equation. The matter wave equation that we developed for the free particle gets us part of the way to quantum mechanics. In 1926, Schrödinger gets us the rest of the way with the Schrödinger equation. He added the potential energy function, which would be 0 for a free particle, and 3 dimensions to solve a broad range of problems. Here is the time-dependent Schrödinger equation, often acronymed as TDSE. IH bar, partial derivative with respect to time of wave function psi of x, y, z, and t, equals operator h hat operating on psi, where h is the Hamiltonian operator, being the total energy operator with dimensions of energy. Notice how dimensions work on the left-hand side of the equation with h bar and the time derivative. H bar has dimensions of energy times time, and the time derivative gets rid of the time component, so we end up with units of energy on the left. H hat is an operator for kinetic energy plus an operator for potential energy. In Cartesian coordinates, h hat equals 1 over 2m times the x direction momentum squared. Now this is an operator. The x direction momentum, p sub x hat squared, plus p sub y hat squared plus p sub z hat squared. 3 kinetic energy operators, plus the potential energy function v of x, y, and z. And we already know how to do momentum operators in terms of spatial derivatives, so the Hamiltonian is minus h bar squared over 2m times the quantity, second derivative with respect to x squared plus second derivative with respect to y squared plus second derivative with respect to z squared, plus the potential energy function. The first expression is the kinetic energy operator expression. The second expression, v of x, y, z, is the potential energy expression for the particular problem we are solving. P sub x hat is the x direction momentum operator. There are cases where the potential energy could also depend explicitly on time. For example, a time-varying external electric field, and then the Hamiltonian would depend explicitly on time. However, we will not cover those cases, which are beyond a first course in quantum mechanics, much less this introduction. For this course, the potential energy function does not depend explicitly on time. However, some of my statements implicitly depend on this. The Schrödinger equation is linear in psi. Psi appears on both sides of the equation. If 2 different wave functions satisfy the equation, then so does any linear combination or superposition of those wave functions. Almost always, we're interested in finding the allowed energy eigenvalues and the corresponding energy eigenfunctions for a given problem whose potential energy is not explicitly a function of time. It turns out that These simplify the Schrödinger equation by neatly separating the time dependence from spatial dependence. If we have an allowed energy eigenvalue E for a given problem, then we can express time-dependent energy eigenfunction, capital Psi of x, y, z, and t, in terms of time-independent energy eigenfunction, lowercase psi of x, y, z, as follows. Capital Psi equals lowercase psi times e to the minus iet over h bar. The time dependence for this time-dependent energy eigenfunction is the complex phase minus et over h bar. Note that the probability density for energy eigenfunction capital Psi is independent of time because the complex exponential of the complex conjugate cancels the original complex exponential, where we're only dealing with an energy eigenfunction. So probability density of x, y, z, and t is lowercase psi star conjugate times lowercase psi independent of time for a normalized energy eigenfunction. The allowed time-independent energy eigenfunction lowercase psi and energy eigenvalue E have to be solved from what's called the time-independent Schrödinger equation, or TISE. And that equation is H psi equals E psi, where H is the Hamiltonian operator, lowercase psi is the spatial wave function, and E will be solved by some energy eigenvalue. We can substitute in the Hamiltonian and we get minus h bar squared over 2m quantity second derivative with respect to x plus second derivative with respect to y plus second derivative with respect to z plus potential energy, all of that quantity times the spatial wave function lowercase psi has to equal the energy times psi. That is the time-independent Schrödinger equation. Note that there are no imaginary numbers in the time-independent Schrödinger equation, and lowercase psi can often be expressed in terms of real numbers without using complex numbers, but the time dependence complex exponential always is complex. Curvature of the energy eigenfunction. Let's restrict ourselves to one dimension and rewrite the time-independent Schrödinger equation so that only the derivative is on the left-hand side. Second derivative with respect to position x of psi equals minus 2m over h bar squared times quantity e minus v of x times psi. Now, at a location x where the total energy is E is higher than the potential energy x, E minus Vx is positive, and so there's positive kinetic energy at that point. The second derivative, this part will be positive, this minus will make it negative, so the second derivative will be a negative number times the wave function. The second derivative shows that the wave function curves toward the axis. This is a classically allowed region. Example wave function curving toward the axis, positive kinetic energy, here is this sine wave. But at a location where the total energy is lower than the potential energy, a classically forbidden region, the second derivative shows that the wave function curves away from the axis. Here's an example portion of a wave function curving away from the axis in a classically forbidden region. This exponential is curving away from the axis. The spatial second-order derivatives sort of measure the spatial curvature of the energy eigenfunction, which is how kinetic energy information is encoded into the eigenfunction. Curvature of psi toward the axis is a negative second derivative and represents positive kinetic energy at that point. The stronger the curvature toward the axis, the higher the kinetic energy. Let's look at the wave function for a more advanced problem. Instead of a infinite square well with completely rigid walls, this is a finite square well. And instead of ranging from 0 to L, it ranges from minus A to plus A. This is a finite well. It's not a particle in a box anymore. This is not the ground state. This is the first excited state. It has one zero crossing within the well, one node. It is a sine wave within the well, but it is exponentials beyond the well. So within the well, it is curving toward, the wave function is curving toward the axis, but outside the well, the wave function is curving away from the axis. Away. Operators, expectation value, uncertainty, and Heisenberg's uncertainty principle. This would normally be a good amount of time in a quantum mechanics course. We're only going to cover it as a brief introduction. Quantum mechanics uses operators that operate on the wave function. These are always linear operators and often include derivatives. Typically, these are shown with a caret or a hat above the symbol to denote an operator. Following are some example operators that are observables because an experiment can be implemented, at least in principle, to measure the value of that operator for a state or a wave function. The exposition operator, x hat, is just multiplication times the value of position, x. But the x momentum operator, p sub x hat, it is h bar over I partial derivative with respect to x of the wave function that we're going to operate on. The energy operator is the Hamiltonian, h hat, for the particular problem. For problems in 2 and 3 dimensions, there are angular momentum operators, and these are important, but we will not cover them. The generalized placeholder observable operator is usually called O, so O hat. The expectation value, which I should show as green, for observable operator O, with respect to normalized wave function capital psi of x, y, z, and t, for a given system, so a given potential, the expectation value is defined as the integral over all space of psi star, psi conjugate, times operator O operating on wave function psi, integrated over all space. This is for a normalized wave function, so there's no denominator. Here, operator O operates on the wave function psi to its right. Operators operate to the right. The expectation value of O for psi, it may be time dependent for a general wave function, but it's generally time independent for energy eigenfunctions. The uncertainty delta O for observable operator O with respect to normalized wave function psi for a given system, it's defined as the square root of the expectation value of operator O squared minus the square of the expectation value of operator O, and that will be greater than or equal to 0. If state capital psi is an eigenfunction of operator O, then the uncertainty delta O for state psi will be 0, and vice versa. There's 0 uncertainty in energy for energy eigenfunctions. The Heisenberg uncertainty principle. For a given wave function, the uncertainty in position for that wave function times the uncertainty in the momentum in that same direction will always be greater than or equal to h bar over 2 for any measurement of x or p sub x, momentum in the same x direction, for any state, any wave function, of any system, any potential. This is always true. It's a very broad principle. The Heisenberg uncertainty principle was discovered independently of the Schrödinger equation, but it was later shown that it is baked into the Schrödinger equation. It is a consequence of the Schrödinger equation due to the fact that operators x and p sub x do not commute, which would be explained in a quantum mechanics course, but we won't cover it. We can never know a particle's position in some direction and momentum in that direction simultaneously to arbitrary precision. The more precisely we measure its position, the greater the uncertainty in our knowledge of its momentum. This prevents the classical assumption that we can know precisely an object's initial position and momentum. In quantum mechanics, we cannot. Particle in a box in one dimension continued. Now that we have more tools, let's fill in some aspects for particle in a box in one dimension, where previously I said we'll see these later. The potential energy function V of x is 0 within the box plus infinity outside the box, so now we have a potential energy function for the Hamiltonian. The Hamiltonian in one-dimensional Cartesian coordinates is minus h bar squared over 2m, second derivative with respect to x squared, plus the potential energy function that we have up here. The time-independent Schrödinger equation is h psi equals e psi, or minus h bar squared over 2m, second derivative with respect to x, plus potential quantity operating on psi has to equal energy times psi. We can solve this differential equation where the potential is 0 between the walls and the wave function must be 0 at the walls, and we get the energy eigenvalues and energy eigenfunctions that I previously declared. If you know enough calculus, you can and should do this and show that it is true. Within the box, the wave function curves toward the axis, and there is positive kinetic energy. Now we want to introduce the time-dependent energy eigenfunction, capital Psi of x and t, for a particle in a box in one dimension. Capital Psi is lowercase psi of x times e to the minus I e sub n t over h bar. This is for an energy eigenvalue, and it's an energy eigenfunction, so there's one energy value, e sub n. So capital Psi sub n is 0 outside the box. Within the box, it's square root of 2 over a. I should make this L. In many places, I copied graphs and equations from an earlier lecture where I used A. So L equals A equals L. So spatial parts times e to the minus I e sub n t over h bar. In this case, both lowercase psi and uppercase psi are properly normalized. Now, we can use our new tools to learn some new things about particle in a box energy eigenfunctions. If we use the definitions and we do the integrals, we will find that the expectation value for x for energy eigenfunction psi sub n is always L over 2. It's the middle of the box, independent of n and independent of time for the energy eigenfunctions. And the expected value of momentum is 0, independent of time and independent of n. We can calculate the uncertainty in position, and there we do get a formula that does depend on n, does not depend on time. The uncertainty increases with n, though it is bounded. Here is the bound for the uncertainty in position. There is an uncertainty in momentum, and it increases without bound with increasing n. Let's calculate the uncertainty product, delta x, delta p. We can just plug in and do the math. We get this formula, h bar square root of pi squared n squared over 12 minus 1/2. It does depend on n, does not depend on time. The uncertainty product is independent of L. It increases without bound with increasing n. The minimum value is for the ground state, n equals 1, and when we plug that in, we get this value, 0.5679 h bar, and that is greater than h bar over 2. So all of the energy eigenfunctions for particle in a box in one dimension, they all satisfy the Heisenberg uncertainty principle. Classically forbidden regions. With particle in a box, we had regions beyond the box that were completely forbidden, in which the wave function was 0. This was a mathematically simple case that helped us begin to learn about quantization of energy and about energy eigenfunctions. However, other problems do not have infinite potential energy hard walls. In this section, let's look at one smoothly varying potential energy, a parabola quadratic, v of x equals 1/2 m omega squared x squared, the simple harmonic oscillator. The potential energy is this blue curve, where this horizontal black line is the 0 for energy. The horizontal axis is position. The vertical black line is x equals 0. The blue curve is that parabola. And we will look at the energy eigenfunction for the ground state energy eigenvalue E0 equals 1/2 h bar omega. This purple horizontal line in energy. Now these red lines, dotted red lines, vertical lines, they are showing us from one graph to the top graph to the bottom graph the points in X where the total energy exactly equals the potential energy. The dashed red vertical lines show the positions at which the total energy E equals the potential V of X. These are the classical turnaround points. A classical particle can only exist between these points, but a quantum mechanical particle can and does have probability to be beyond these points. This green curve is the energy eigenfunction for the ground state energy for the simple harmonic oscillator. Note that it has non-zero value outside of the dotted red lines. So let's note some things. The green wave function, the eigenfunction curve, curves toward the axis between the dotted red lines. The particle has positive kinetic energy in that allowed region. The green eigenfunction curves away from the axis beyond the dotted red lines, the classically forbidden regions. So from here to here, it's curving toward the axis. Here it's curving away, and here it's curving away. The green eigenfunction curve tends to 0 at plus or minus infinity. The particle has finite non-zero probability for being anywhere in space, but the probability decreases rapidly further from the center of the binding potential. Tunneling through a barrier. In classical mechanics, a particle cannot cross a potential energy barrier higher than its energy. In quantum mechanics, there's always a probability for crossing or tunneling through any finite potential barrier. Here's an energy picture. The position is horizontal, vertical is energy. The black curve is potential energy, 0 potential energy, and then all of a sudden a barrier, and then back to 0 potential energy. The dotted blue curve is some energy for some particle. This particle is moving left to right. It is actually moving. Far to the left, the particle is unbound. It's not a free particle. It's a free particle on the left of the barrier, and it has some kinetic energy, and it's moving toward the barrier. And within the barrier, the energy of the particle is lower than the potential energy, and so classically the particle would not be able to be there, but quantum mechanically it can be there. And then we're not quite sure what would happen on the right. If the particle could be on the right, it would again be a free particle, and it would be moving to the right with this amount of kinetic energy, if it can. Now, the wave function looks like this. For a free particle, so this is the spatial component of the wave function. I'm not showing the time dependence. The spatial component of the wave function looks like a sine wave to the left of the left barrier and is curving toward the axis, positive kinetic energy. But in the barrier region, the wave function must curve away from the axis. It must be an exponential, and it is. But look, here's a solution where there's a little sine wave on the right, curving toward the axis, and this wave function is continuous. This sine wave matches up perfectly with this exponential, which then matches up perfectly with this little sine wave. This is a valid solution for a particle tunneling through that finite energy barrier. We are not going to work out the details. Tunneling is used in certain electronic devices, some electrical effects, and to explain the half-lives of nuclear radioactive decay. Why are the energies of bound states quantized? This might occur to you on a philosophical level, but it also might occur to you if you're a mathematician or were a math major. And we will see why. The time-independent Schrödinger equation is a second-order partial differential equation. In one dimension, it's this equation, minus h bar squared over 2m, second derivative with respect to x, plus potential energy operating on the wave function psi equals energy times psi. Well, for a moment, let's look at this just mathematically, not as a physics equation. For a given potential energy function V and a given total energy E, any energy E at all, the wave function, lowercase psi, should be mathematically completely determined given two initial conditions. For example, the value of psi and its first derivative at some point. It's a second-order differential equation, so it only needs two initial conditions to determine the solution. Now, this is if we view the energy E as given, not to be determined. Now, okay, maybe we can't solve it algebraically, but we can always solve it numerically on the computer. That's always possible. So we might naively think, well, gee, that means that we could have any energy at all, and there would be a mathematical solution. And that's true up to a point. However, in addition to the potential energy function, we have some physical constraints which become mathematical constraints. These physical constraints, the effect of them is to discard the continuum of possible mathematical energies and leave the certain discrete quantized energy for a particle bound by a potential. For a particle in a box in one dimension, the physical constraints are that the potential is infinite outside the box and the wave function must be zero at the walls and outside the box. And the wave function must be continuous inside the box. Let's look at the valid energy eigenfunction, which I'm going to show as a green curve, for the ground state of particle in a box, and also two physically invalid wave functions corresponding to 20% more energy, the red curve, and 20% less energy, the blue curve, than the ground state. The green curve for the physically valid energy eigenfunction for the ground state of particle in a box, it has zero value for the wave function at the left hard wall and the right hard wall, as it must have to be a valid physical solution. Now, I've made the red and blue mathematical non-physical solutions. I've made them be zero at the left hard wall, but I haven't constrained them on the right hard wall. The curvature is due to their energy. The Red curve has more energy than the green curve, so it has more curvature toward the axis. The blue curve has less energy than the green curve, so it has less curvature toward the axis. And when we get to x equals L, those wave functions do not have value 0 at the right hard wall. The blue curve has lower energy than the green curve, less curvature toward the axis, but the wave function is not 0 at the right hard wall. This solution for the energy is not a physically valid solution. The red curve has higher energy than the green curve, greater curvature toward the axis, but the red wave function is not 0 at the right hard wall either. This solution for the energy is not a valid physical solution. The two hard walls force the energy to be quantized in definite specific energies, not continuous, for a particle in a box. But generally, we do not have hard walls or infinite potential energy. For bound states, we always have the physical requirement that the wave function tend to 0 at plus or minus infinity. This is needed to make sure that for a binding potential, we have less and less probability of finding the particle infinitely far from the potential, from the origin of the potential. This condition forces the energy to be quantized. Far from the origin of the binding potential, E minus V of x is negative and large, and so minus 2m over h bar squared E minus Vx is positive and large. The magnitude of the second derivative, it'll be positive and large except for the special case where the wave function tends rapidly to 0 as magnitude of x grows, which is only going to be true for one of the quantized energy eigenvalues. Energies that are not the energy eigenvalues give rise to exponential functions that grow without bound instead of tending to 0 at plus or minus infinity, something like the following for the quadratic potential. I'm only showing half of space here. I'm starting with x equals 0 and going to the right to positive x. The vertical axis is the value of the wave function. There are three energies, green, blue, and red, and I started their wave function all at value 1 and slope 0, derivative 0 at x equals 0. The green curve, it's for the physically valid energy eigenfunction for the ground state of the quadratic binding potential. It has the wave function tending to 0 at x equal plus infinity, as it must to be a valid physical solution. But the blue curve has lower energy than the green curve, less curvature toward the axis. If we look around here, we could see that it has less curvature toward the axis. Within the bound region near the origin, but the wave function blows up at plus infinity. This solution for this energy is not a physically valid solution. This blue case is not an energy eigenvalue and an energy eigenfunction for this potential. The red curve has higher energy than the green curve, greater curvature toward the axis within the bound region near the origin, but the wave function blows up at plus infinity. In this case, it blows up as minus infinity as x goes to plus infinity, but it blows up. This solution for this energy is not a physically valid solution. This red case is not an energy eigenvalue, an energy eigenfunction for this potential. The green energy is an energy eigenvalue and energy eigenfunction for this potential, but the nearby blue and red energies are not energy eigenvalues and energy eigenfunctions. The continuum of energy values are generally not physical energy eigenvalues. Only certain definite energy values are energy eigenvalues for a given binding potential. This is the end of the second of 4 videos for this course.